Hi, I am Tarun. In this project, I am working on battery data analysis and prediction using machine learning. The goal is to clean the raw battery data, remove anomalies, engineer useful features like state of health and remaining useful life, and prepare the data for training advanced models. Creating data folder and loading files. First, I create a folder named data using the OS module. Then I list all files inside this folder to confirm that the dataset files are available. These files are NASA battery datasets stored in .mat format. Extracting battery data. I define a function called extract battery, which reads the .mat file using SkyFi. Inside this function, I access the battery structure and loop through all cycles. I only select discharge cycle because they are important for analyzing battery degradation. From each discharge cycle, I extract voltage, current, temperature, and capacity values. Then I compute the mean of voltage, current, and temperature and store them along with capacity in a list. Finally, I convert this data into a data frame combining multiple batteries. Next, I apply this function to multiple battery files like B0005, B0006, B0007, and B0018, B0018. I combine all these data sets into a single data frame using td.contact by using pandas concatenation. Anomaly detection. Hmm. Anomaly detection. To clean the data, I use a isolation forest model. This is an unsupervised machine learning algorithm used to detect outliers. I set parameters like number of estimators and contamination level. Then I fit the model on the dataset and label each data point as normal or anomaly. I remove the anomalous data points and remove the anomalous data points and create a clean data set. I also print how many data points were removed and visualize anomalies using a scatter plot. Advanced dataset loader. I also these colored points other than yellow are anomaly points. Advanced dataset loader. I also define another function called load NASA battery data. This function loads detailed battery data including voltage, current, temperature, and capacity at each time step. It creates a structured data frame with battery ID and cycle number, which is useful for time series modeling. Feature engineering. In this step, I create important battery health features. First, I calculate state of charge or SOC by normalizing capacity within each cycle. Then I calculate state of health or SOH by comparing current capacity with initial capacity. Next, I compute remaining useful life or REL, which tells how many cycles are left before the battery reaches end of life, defined as SOH dropping below 80%. I also create additional features like power and voltage current interaction to improve model performance. Sequence creation. To prepare the data for deep learning models like LSTM, I convert the data set into sequences using a sliding window approach. I scale the features and target values using min-max scalar. Then I create input sequences of pixel length and corresponding output values. This helps the model learn temporal patterns in battery behavior. Model training utilities. I define helper function for training and evaluation. The get callbacks function includes early stopping and reduce learning rate to improve training efficiency and avoid overfitting. The evaluate model function calculates performance matrices like mean absolute error, root mean square error, and R square score to measure how well the model is performing. Conclusion. In summary, this code performs data extraction, cleaning, feature engineering, and sequence preparation for battery health prediction. It sets up a strong pipeline for applying machine learning and deep learning models to predict battery performance and lifespan.